Here's an overview of ideas from Chapter 5 involving thermal chemistry. We began the chapter by looking at the concept of energy in different ideas such as heat, work, and describing systems, closed, open, isolated. Here were different symbols that we had that we needed to make sense of. Q, W, E, where we're looking at things like the heat, the work, the internal energy, potential energy, kinetic energy, what the temperature was measuring. So consider this. I see a pot of boiling water. Use this scenario and try to explain every term. Can you make connections across those? That's a great way to summarize your own understanding. And if you're having trouble, which terms do you find confusing? In class, we analyzed this experiment where we considered an Erlenmeyer flask with water, a balloon fixed on top, and it was placed on a hot plate. And we described the balloon, the Erlenmeyer flask, and the water as a closed system. When we looked later, this was what the system then looked like. The task, what would be the sign of Q? What is the sign for W? And is this endothermic or exothermic? Give that a try. I would say Q is positive, heat is going into the system. Work is negative. The volume of the system increased. PV work was done on the surroundings. When I have generation of moles of gas, great indicator that the work is going to be negative because it has a potential then to do PV work on the surroundings. Endothermic or exothermic? It's endothermic. That's referring to the heat. We also made sense conceptually of diagrams like this, showing the potential energy for charged particles and connected those to chemistry ideas. Can you make this connection? Here's an end of chapter question on this topic. And here's another one that I generated. Can you answer this question? Give it a try. Moving on, in 5.3 and 5.4, we looked at the topic of enthalpy. Here are characteristics of enthalpy as an extensive property. If we change the reaction, the direction of it, we will change the sign, but not the magnitude, and it's a state function. When we're looking at an enthalpy change, that's a heat transferred at a constant pressure. Here are sets of questions that are both conceptual and connecting enthalpy to stoichiometry. Hess's law is an application of enthalpy being a state function. Here are a few examples of Hess's law questions. These are really easy to identify and I think useful to practice. The topic of calorimetry. That's where we introduced ideas like heat capacity and specific heat. And oftentimes we looked at scenarios. Here was one such scenario. This one's involving heat capacity. Notice the units are kilojoules per degree. So a few questions for you. Given the scenario, how much heat was produced? How much heat was produced per gram? And how about then per mole? I'm going to be looking at the change in temperature and using the heat capacity to figure out the amount of heat that was involved. That can be scaled per gram or expressed per mole. In this case, I see the temperature going up, so I know it is an exothermic reaction, and so the enthalpy change has a negative sign. Here's another scenario and some leading questions for you. Give this one a try. As I look at this, is it exothermic or endothermic? I'm going to look at the thermometer. It got colder, that corresponds to endothermic. The heat that was involved, I need to use the specific heat. It says to use the specific heat of water. The mass that is involved is the total mass of the solution, both the water and the sample that dissolved in it, and I have a temperature change. That'll tell me the amount of heat that was involved. And then I'm reporting it in kilojoules per mole of the ammonium nitrate. So let's figure out how many kilojoules per mole that corresponds to. And this would have a positive sign because it's an endothermic process. How do I know that? Again, I looked at the thermometer. Here's a few scenarios if you want to give calorimetry questions a try. Moving on to enthalpies of formation. Two different skills there. We need to identify a standard enthalpy of formation reaction and then use provided data. Take a second to see if you can answer these. Which of these represent standard enthalpy of formation reactions? And if they're not, can you improve them so that they are appropriate? What I'm doing in this case, I'm going to look at the products. For a standard enthalpy of formation, I'm expecting a single product with a coefficient of 1 corresponding to 1 mole. I'm going to look at the reactants. Fractional coefficients are okay. And I'm going to have the elements in their standard state. How would I summarize this topic so I remember it? I would write 2 or 3 examples that illustrate the concept. Here's sample problems if you want to give it a try. For any one of these, you should be able to write the appropriate standard enthalpy of formation reaction. We use that data within our setup here, where we're interested in the total standard enthalpy of formation values for the products minus that of the reactants. With provided data, we could come up with an overall enthalpy change, or perhaps we have the overall enthalpy change and we're interested then in identifying one of the internal either reactants or products. Here's example problems. We just need to be careful, account for the coefficients, and it's products minus reactants. Moving on to bond enthalpies. Another case where we would have provided data, and we're conceptualizing it as if we're taking apart the molecules and then putting them back together. The taking apart portion, that would be endothermic. It always takes energy to break bonds. Exothermic within the bond formation. That can also be conceived conceptually. Question 5.82, without doing any calculations, predict the sign for the enthalpy change. That's one that you can give a try. I think we've also added skills to be able to draw various molecules. So given that balanced equation in the provided average bond enthalpy data, I think we could now write the corresponding structures and use the data to come up with the overall enthalpy change. Similarly, with these two examples, I think we could even take a word description, write the balanced equation, and then write the appropriate molecules. Give that a try. Here would be the both the molecules and the appropriate coefficients. Here's a combination, once again, where we can be predicting enthalpy changes. Are there any of these that you find confusing? So within this whole set, I think within Chapter 5, we have a combination of concepts and then also calculations. In both cases, I think it's important to transform the instructional material, practice the problems, and summarize it in a way that makes sense to you.